along to an unusual video today, and instead of being something to do with cars and go-karting or the BMW M5, today we're looking at a classic British Rail Class 91 locomotive which is currently in service, and we are at Neville Hill Traction and Rolling Stock Maintenance Depot, where we'll be taking a close look at 91107 today and giving an in-depth view of the sort of thing that I go through when running training courses on these locomotives and what information I would give to traction trainees. It's not going to be as in-depth as what we would expect, because end of the day you're not all traction trainees. It's just going to be a nice overview of what goes on in the driving cab and within the engine bay as well, or equipment room if you prefer. So we're starting off in number one driving cab. How do we know it's number one? Well, it's the business end of a train, it's what we normally drive in from. The locomotive has two driving cabs, A and B, or 1 and 2. And the speed from number one driving cab is 125 miles an hour when attached to the appropriate rolling stock, and from number two cab it is 110 miles an hour, and that is due to the design of the body profile of the locomotive. Number one end is more aerodynamic, it's got a approximately 40-degree raked front end, and whereas number two end, which is commonly attached to the coaching stock, is a pretty much slab end. It's like, has the aerodynamics of a church. So we have to do 110 mile an hour if we're driving from that end, due to the aerodynamics and the issues it can cause with the pantograph system. Pan bounce against the overheads, which could subsequently cause damage to the pantograph or the overheads. Control wise, both driving cabs are almost identical. Number one cab has been modernised over the years, as we can see. So we've got a adjustable Chapman driving seat. Down on the left hand side we've got, starting from left to right, we've got the TMS and VMS alarm, and that system monitors the traction motors and gearbox and cardan shafts for excessive vibration, noise, motor mount failures and things like that. So if we get that alarm go off, it's pretty serious. We'll be having to stop the train and go deal with that. We've then got our overhead voltage, which gives us a general idea of how many volts are coming into the locomotive from the overhead. Nominal 25,000 volts. The locomotives will run down to around about 17,000 volts before we start having issues. Once it drops below 19,000, the air conditioning in the driving cab turns off, and there's a few locations en route where that happens. If it starts dropping further, the locomotive starts surging, and you can feel the loco trying to drive and pull along, but there's not enough power coming into it to maintain that tractive effort, so it starts surging. We have a status panel which gives us a brief overview of some of the critical systems within the locomotive if they're operating correctly, such as traction motors, the transformer oil pump, converter oil pump, air compressors, data recorder and some other safety systems. We've then got the driver's control panel for parking brake, brake overcharge, heating and ventilation, external and internal lighting and window demisters. Not a lot on there to discuss. Keeps us warm, keeps us cold, stops the locomotive rolling away. Directly in front of it here we have our master brake controller, or the service brake controller, and when that's used it operates the air brake pipe along the entire length of the train in its most simplistic format. We remove air from the air brake pipe to allow the brakes to operate on the locomotive, coaching stock and driving van trailer, and the brakes operate via a little unit called the brake distributor, and that essentially is two separate chambers, one with pressurised air for applying the brakes, one with pressurised air for keeping the brakes off. So if the air brake pipe drops from 5 bar towards 0, so 0 is an emergency application, 3.5 bar or thereabouts is a full service, and 5 bar is release. So anything in between 5 bar and 3.5 bar is our normal use. So if the air brake pipe drops between them, then the distributor converts that into a positive air pressure to allow air down to brake actuators on the vehicles to apply the brake pads to the brake discs, generating heat and a transfer of kinetic energy into heat, thus retardation of the consist occurs. We also have the direct air brake immediately behind that, and we don't use that normally when we're driving the locomotive unless we're driving the engine on its own. It only controls the brakes on the Loco. So directly in front of the driver we have our 5 bar air brake gauge, we have our speedometer with the speed set chevron at the top, driver's reminder appliance, TPWS equipment, and our fault lights. Each one of these fault lights is yellow under normal circumstances, and if it detects a fault, or the locomotive detects a fault, then it goes red. And that alerts the driver to an issue that may be within the locomotive, whether it's internal, external, or something to do with the overhead power supply. A little bit further over to the right we have our onboard radio equipment, our GSMR, electric windscreen wipers and washers, external hazard warning lights, communication between the driver and the guard, and various buttons for raising and lowering the pantograph and overriding certain safety systems which would prevent the train from continuing in an emergency. So if the fire system activated in an emergency, we have a button where we can press. That'll give us limited amount of time before we lose our overhead line supply to the locomotive to allow us to drive the train to get it somewhere where we could deal with a fault, i.e. not inside a tunnel, cutting, or on a viaduct, somewhere like that. Down here we have our direction selector on there, there's warning horn and the power controller. It's only a dainty little power controller on the locomotive, but it's controlling 6,075 horsepower via an electrical converter cubicle in the equipment bay, which we'll show you shortly. Number 2 driving cab on the locomotive is pretty much as built as it was in 1989. The driving controls are identical, they're just laid out a tiny little bit different. So all the switch pack on this side is as built, as is the dashboard, and we've still got the British Rail Engineering logo for Crew Works where these things were built. And on the bulkhead behind us we can then go through the equipment bay door into the engine room / equipment bay to observe the equipment in here. So we'll walk through and you'll see that it's pretty cramped. And then when we get down to number 1 end, we'll have a look at some of the equipment and work our way through it. As we go through the bulkhead door from number 1 cab into the equipment bay, the first thing we will see on the left hand side is our fixed firefighting equipment, which consists of 3 Argonite bottles, pressurised between 150 and 220 bar, nominally 200 bar. If the locomotive detects a fire within the equipment bay, then these will automatically discharge and alert the driver via a fire alarm. On the bulkhead behind us we have our TPWS temporary isolation switch and our motor brake switch down at the bottom. The motor brake switch essentially allows you to get power without the brake applied, but will also knock off power if the brake is applied in its most simple format. We then have On the right hand side and left hand side, traction motor blowers. So we have traction motor blower number 1 and traction motor blower number 2, and associated smoothing chokes 1 and 2, and then the traction motors are underneath the locomotive, and they're kept nice and cool by these traction motor blowers. If one of the blower motors fails, the traction motor detects it, as does the equipment in the loco, and then self-isolates after alerting the driver. Next up we have our MPU cards. This is essentially a computer from 1980s. So we've got various control cards in here with LEDs lit up. Any of them LEDs turn red denotes a fault within a certain system, and then maintenance control can ask us which system it is that's gone down based on the information on the MPU card and which light numbers lit up. On the right hand side we've got an electronics cubicle. We have no access to this, it's just full of electronics and magic. Next up on the right we have our rheostatic bank for number 1 bogie, and that allows the traction motors to be used as brakes. So it reverses the polarity on the DC traction motor, sends electric up into the rheostat, which is then burnt off as heat and ejected out of the ceiling of the locomotive, which is why you may see a heat haze coming from the top of the locomotive on a warm summer's day or a cold winter's day. The rheostats do work really hard. On the left hand side we've got our TDM communication panel and data recorder within a cupboard. Inside this cupboard is a light which very helpfully illuminates his way. So this TDM system is essentially the communication between the locomotive and the DVT, the driving van trailer, which allows the locomotive to be remotely controlled and driven from elsewhere on the consist. The data recorder records absolutely everything that we do and is used in accident investigation or incident investigation and for monitoring and assessment of drivers. On the right hand side here we've got our transmission fail-safe detection system, status panel. Normally the safe set is lit up green to indicate that it's working normally. If it detects a fault on the traction equipment, on the traction motor itself, or the axle and the quill tube, then we get an alarm in the driving cab and we have to stop the train and go deal with that. On the left hand side here we've got our converter cubicle, which contains all the high voltage electronics and electrical circuits for making the locomotive stop and go through the rheostatic brake and the traction equipment through driving. And we also have in here the thyristors, which you can see in there with the associated equipment as well. All very high voltage. We also have a gauge in here for the transformer. So the transformer contains 1500 litres of oil with approximately 20 litres in a header tank, and the gauge monitors the header tank. If it runs low, it detects that, opens the VCB on the locomotive, and it goes into self-preservation and protection mode. This big box on the left hand side with a spare pantograph on the top. That is our air conditioning for the equipment bay, as it needs to be kept at a nice set temperature in here. Passing through we have our radiator blowers just behind the converter cubicle and behind the equipment bay air conditioning. So B side number 2 and A side number 1, and these are what you hear when the locomotive is just about to set off. So when we select as direction, these radiator blower fans start operating and blow cold air down to a transformer through a plenum, and that keeps the transformer nice and cool and below 65 degrees Celsius essentially. If it gets to 65 degrees Celsius on a red hot day, these fans will run constantly to try and cool down the transformer. If you get to 85 degrees Celsius, then we're in game over territory. The locomotive will go into self-preservation mode and open the VCB to prevent the transformer being cooked. And it's then a case of haulage out of the way with another locomotive. On the right hand side, we now have our Davies and Metcalf brake frame, also known as the E70. That contains the equipment for the control of the locomotive brakes and the train brake pipe down the red pipe through the consist, and also the distributors for the locomotive as well. On the left hand side we have our battery charging equipment at the bottom and our pancake air filter for the two main air compressors. The big red pipe here is our digital diesel, that's your 25,000 volts coming through from the overheads via the pantograph into the transformer. This small piece of kit here is a spark arrestor. So should the locomotive be subject to a lightning strike, then the spark arrestor will automatically operate and send that lightning strike and the current it creates direct down to the railhead and out through to earth to prevent damage forming within the locomotive systems or toasting the transformer. This big box here is our control batteries at the top and our field batteries at the bottom. Control batteries, 110 volts, everything to do with the control of the locomotive. The field batteries is for allowing the traction motors to remain as a rheostatic brake when we traverse through a neutral section and we lose this overhead line supply, and it will give us around about 15 seconds of rheostatic brake when the overheads aren't available. It will then revert back to friction brake through this module here called the blender, and blending the friction brake on the locomotive. Next up, above the battery bank, we have our pantograph frame. So this is the air system which controls the pantograph, and the auxiliary compressor which allows air to be generated or created to raise our pantograph. So we've got two safety systems on here, the automatic drop-in device and the fast automatic drop-in device. Should they detect a loss of air pressure within the pantograph, then it will automatically lower the pantograph to prevent damage, such as a chip in the carbons, or if a piece of overhead line equipment has damaged the pantograph itself elsewhere. We then have the circuit breaker panel and control cubicle. The top two rows of circuit breakers are our 110 volt DC equipment. We then have some flagged relays which are essentially circuit breakers, but if a piece of equipment has overdrawn current but not to a critical state, then one of these relays will trip for maintenance to then observe and go rectify the fault. And then down at the bottom we have our 240 volt big equipment circuit breakers. So there's traction motors, there's radiator blowers, oil pumps for this transformer, and so on and so forth. Here we have the cubicle for isolation of equipment. So we've got our AWS, TPWS, DSD, our traction equipment isolating for rheostatic brake, and the bogies for isolating traction motors on a bogie by bogie basis, and then our air compressors. A couple of voltage gauges for our control batteries at the top and our field batteries at the bottom. If for any reason when we're setting up the locomotive from dead, after it's been stabled overnight with a pantograph down somewhere, and the control batteries are below 85 volts, we can then operate the battery volts power button, which will basically link the field batteries to the control batteries in parallel and send the voltage across. Very much like a split charge system on your camper vans and motorhomes and things like that. Next up we have the traction motor blower equipment for number 3 traction motor and then number 4 traction motor. Again, air blowers, smoothing chokes, down to the traction motors, keeps them nice and cool. And last but not least, but by most way it is probably the most important piece of kit, we have our parking brake frame, our hydraulic parking brake, where we apply via an electric pump the parking brake to secure the locomotive when we stable it, and release via an electric pump as well. If that pump becomes defective for any reason, then we can manually operate the parking brake and check that it has applied at this location or released. So that concludes the tour of the engine room. As we walk back through towards number 1 cab. And we will now have a look on the outside for the traction motors and associated equipment. Underneath the locomotive we have got our 4 traction motors underslung from the body. They are not directly mounted to the bogie frame. The bogie frame is completely independent of the locomotive and only contains the Voith gearbox and the wheel sets and brake equipment and associated suspension. The motors are underslung and held on by 4 big motor mounts, 1 on each corner. And on the free end of the traction motor we have a brake disc, which also acts as a kinetic energy store as well, essentially like a flywheel on your car. On the driven end of the traction motor we have a cardan shaft, which is spring loaded and under hydraulic pressure. So if for any reason the traction motor overcomes the hydraulic pressure within, then what is known as protractor bolts fire. They are located down here. Then that releases the oil pressure from within the cardan shaft and demeshes a mechanical drive inside and turns it into a free spinning portion of the cardan shaft. Essentially it disconnects the transmission from the traction motor to prevent damage. And if that happens, the big piece of equipment here monitors for that, and we will have a notification within the driving cab that has happened. On the back of the wheel, you can see at the opposite side we have our integral links. We also know these as our dog bone links because they look like dog bones, and that is picked up if there's defect through the vibration monitoring system within the driving cab as well. So if the axle develops a vibration outside of a given tolerance, then the system activates in the driving cab, we have an alarm and we have to apply the braking to emergency and come to a stand. Underneath the locomotive, in between the bogie frames, we have our 2 air compressors at number 2 end of the locomotive and our transformer towards number 1 end of the locomotive. As we've discussed already, the transformer is underslung in 1500 litres of oil and is kept cool by the radiator blowers forcing air into the plenum, and the plenum is what we can see here, just the bottom of it. The rest of the transformer is inside there, we can't see it. The transformer has some protection built into it as well. It has a Buchholz and a Qualitrol system to detect and prevent overgassing, overpressurisation and low oil level as well within the transformer. On the outside we have our battery isolation switch. It is a 4-position switch, 2 on, which are side and side, and isolate at the bottom and off at the top. When it's in isolate, the locomotive is dead. When it's in off, certain systems still operate, such as fire detection, end lighting equipment and cab lighting equipment. We also have fixed firefighting equipment on the locomotive which we can manually operate. These consist of nitrogen bottles. We have one in each driving cab of the bulkhead and one on each side of the locomotive just behind number 2 bogie. These have a nominal pressure of 50 bar. If it's any lower, then the system won't operate, and if that little flap is pulled and a lever inside there is operated, it then sends that nitrogen pressure to the argonite bottles inside the locomotive, which then discharges the argonite bottles into the engine room. Number 2 bogie looks identical to number 1 bogie, and then we get to the vehicle end where we have our connection to the coaching stock. So as you can see, the buffers are in the retracted position, and the buffering is now done by the rubbing plate between the locomotive and the trailer open end vehicle, the TOE vehicle, and the mechanical connection itself is done via the drop head buckeye. For electrical connections, we have our ETS cable, then our UIC cable, that is repeated on the opposite side. The corrugated plastic cable is the Ethernet cable or Icomera, and then we have our pneumatic cable connections of the yellow 7 bar train pipe and the red 5 bar brake pipe. On the outside of the locomotive at the front we have some standard equipment. We've got retractable buffers, a rubbing plate, a drop head buckeye, 2 train pipes for 7 bar and 2 brake pipes for 5 bar. We also have an ETS receptacle at each side and a UIC receptacle at each side. The ETS is supplied down the train at 1000 volts, nominal with a proving cable. Should the proving cable become disrupted or one of the ETS flaps become open, then the ETS will disengage on the locomotive. The UIC cables transmit down the train the TDM system, which is the remote control from front to back, and the FDM system, the frequency division multiplex, which in its most simplistic terms is our door interlock proving circuit. The buffers on the locomotive are retractable, so normally we run with them in the extended position, so you can see them sticking out just in front of a rubbing plate. If the buckeye was raised and in use, then the buffers would be retracted by lifting the drop pin, spinning the buffer through 90 degrees and pushing it in, then push the drop pin back in so it locks into that groove on the sliding portion of the buffer. That would then allow the rubbing plate to absorb the impact and buffering of the coaching stock to the locomotive and the buckeye to do the mechanical connections. So that concludes our brief overview of the Class 91 locomotive. Hope you found it informative. As I say, it's not something we normally do on this channel. I'm in a unique opportunity where I'm delivering driver training on these, so I get to be able to do things like this. So some of this material will work its way into our training material as well. If you've liked this, give it a like, subscribe to the channel, ring the bell and all that other good stuff. Then we'll be back soon with some more M5 videos and getting back on track at Donington and Cadwell and the Nürburgring. So we'll catch you later.